All right. Good evening, everybody across South Africa. Good evening, iPlaneteers, and welcome again, once again, to the second of our three Habitable Planet live online events as part of HPW19. It's great to once again get everybody together. I hope everybody is comfortable and you have your pizza in your various locations across the country. And so to kick us off, it's me. I just have a couple of announcements for the people doing the course before we press on and we go and start looking at the physical, not the physical, the chemical and biological reasons why Earth is habitable. Okay, so from me, before we start, I just wanted to answer some of the more general questions that we've had on the course and some sort of little admin issues. The first one is that lots of people have been asking about the face-to-face workshop that's coming up, how you get on it, and when it is and where it's going to be. So just very quickly to clear those up, the workshop has actually been moved. This is new. This is it's hot off the press. The workshop has been moved. It's now going to take place in Cape Town. We will be visiting and taking you to Table Mountain and seeing the mother city. It will be the 5th to the 15th of December. And just want to point out that having looked at all of the marks so far, basically anyone can still come. So it's all about those exam results. It's about filling out your climate record and getting top scores. The top 30 or so people from the course will be coming with us to Cape Town to do all that kind of stuff. So it's really important, keep filling out the exams, make sure you fill out your climate record, and hopefully, if you do well, you'll be one of the 30 coming to Cape Town. Okay, so that's the trip to Cape Town. I just wanted to remind you that this is an interactive session. So it's all about you guys. We're going to try and answer your questions. But if you want to ask questions during the session, that's more than welcome. And obviously, it's even better because it can catch our scientists off guard. So you can do that with Twitter. You all know there's the hashtag HPW19 for Twitter. Go to our Facebook page, or if you like, you can just give us a classic old email to Redani. All of you have Redani's email address. Okay, so the questions this week are all on the physical and biological reasons why the planet's habitable. The first thing I want to say about this week's questions is that the questions you guys have sent in have been incredible. I've had almost all of the scientists assembled email me or comment to me that these questions have been really interesting. So we're really, really excited that you guys have asked these and really keen to get into them. The one thing I will say about your questions is that, guys, you keep talking about this thing called humans, right? Everybody keeps asking about humans. We haven't introduced them into our model yet. We did physical stuff. We've now done plants and biodiversity, and we've done chemistry. We haven't mentioned humans. But seeing as you seem to be so keen on these human things, I am going to allow some questions on humans this week, so long as they relate to the topics. But remember that actually in the next few weeks of the course, we start to introduce humans into our conceptual model of the Earth, and that's when we'll really be able to do the human questions. The last thing is that a few people have been asking about how they continue to be involved in Access. And I just want to say, I have put out adverts for you guys to become core lecturers or to run schools programs. So have a look at those. Those are ways in which that you can carry on. So without further ado, I'd like to introduce to you today's panel. I am going to go around the room. I will start with Redani here in Cape Town before heading out to the rest of the country. I'd ask the panel members, please, if you could just very briefly introduce yourself, what your specialism is, and then I'd like you to tell our students what the strangest thing you've ever had to do in the name of research is. So Redani, can you kick us off?
Good evening, everyone. My name is Redani Mulaudzi. I'm from Access Education and Training Portfolio. My area of specialty, I've been involved in behavioral ecology of primates for 5 years, from 2010 until 2014. And I've changed gear now. My research interests are more into climate science communication. I'm currently pushing my PhD proposal, for which I'm going to register next year. The strangest thing that I've ever done, one of them, is it's a bit funny. I spent six days without having a contact with water while on a research, working on a research project in Madagascar at a place called the Mikia Forest.
Okay, thanks Redani. Okay, Mike, over to you.
Hello, good evening everyone, and good afternoon to those of you in America. My name is Mike Lucas. I'm an ocean biogeochemist working at the University of Cape Town, and I guess my speciality these days is the role of climate change and the oceans and the interaction between oceans and climate. And I guess one of the, I'm basically an oceanographer in many respects. I've spent 30 years going to sea on ships all over the North Atlantic, the South Atlantic, the Southern Ocean. And I guess one of the most curious things that I've done in the name of science was when I was a postdoc student at Duke University in North Carolina, and one of the guys' project was to assess the mortality of the use of vehicles on sandy beaches, to look at the mortality of ghost crabs when vehicles were being run down the beach. And his project, funded by the National Science Foundation, involved two quad bikes. The first guy would ride down the beach randomly, I suppose, and the second quad bike would follow after him to see how many corpses there were, how many deaths there'd been due to the quad bike. The answer was 0, because ghost crabs are very fast. If you've ever tried to catch one, you can't run as fast as a ghost crab. And the other thing is their burrows in the sand are quite deep, so quad bikes weren't getting deep enough to worry them. But for me, that was one of the more bizarre projects I've been involved in.
Thanks very much, Mike. You guys, I think you all know me. My name is Carl Palmer. I'm an atmospheric chemist by training, and I work at Access. And the strangest thing that I ever had to do was, I think, rescue one of my students who nearly drowned after swimming out to get a water sample. I had to be rescued and then taken back in an ambulance.
Hi everybody, my name is Godfrey, and I'm by profession I'm a geneticist. Well, profession, and I'm now no longer a geneticist. I'm an immunologist. So I think the strangest thing I've ever done so far is to switch between disciplines so fast that sometimes I get lost in what actually I'm doing. So, but that's pretty much me in a short nutshell.
Thank you, Godfrey. Raissa?
Hi everyone, I'm Raissa, and like Mike, I'm an ocean biogeochemist. At the moment, I'm looking at how the interactions between iron and light limitation for phytoplankton growth in the Southern Ocean. I don't think I've really done many strange things, but well, or maybe I'm too strange and I don't know. But one of the things I've thought about is that on one of the research cruises, I had to lie down on the deck with bright ons to try to rescue my samples, not my students. So I guess that's really strange.
Thanks, Raissa.
Can you see me?
Dr. Sweijd.
Hi. So I'm Neville, and I'm the director of the Access program. And if I'm anything, I'm a biologist. My PhD was in the genetics, application of genetics in marine science. I worked on abalone. But now I do all sorts of things, and my latest interest is actually in the relationship between climate and public health, which is an area which I'm very interested in and getting more and more involved in. And a strange story for you, well, I have too many to choose from, but I thought of one which is relevant, which might be a lesson to you all. And I spent for my PhD collecting samples all along the coast of South Africa, which was a very expensive thing to do, to go with a whole bunch of divers and equipment and planning and vehicles and accommodation costs and liquid nitrogen and all sorts of sort of specialized effects and tools and effort, only to discover that Morgan Bay and Mossel Bay both have the initials MB. And so when I took my samples out of the liquid nitrogen, I couldn't tell which samples were from Mossel Bay and which ones were from Morgan Bay, which was a very serious problem because basically the money was wasted, at least in those two cases. But we overcame the problem with genetics in the end. That's me.
Science came to the rescue.
Yes.
That's all it is. All right, I'm going to start with the people not in Cape Town. I'll go furthest away first. So Chris in Atlanta, would you like to just introduce yourself?
Okay, hello everyone. My name is Christopher Bennett, and I am at Atlanta, as Carl said, at the Georgia Institute for Technology. I was previously with the NASA Astrobiology Institute in Hawaii for about 10 years, where I studied the interaction of radiation with ices and how you can form biological molecules. Since I've come to Atlanta, I've been working still on that project, but also in more planetary science. I've been working with the chemical Center for Chemical Evolution on the formation of peptides in an early Earth environment. So I don't feel like I have many interesting stories about what I've done for research, unfortunately. The closest I get, I guess, is when I went to China. I was very fortunate to be able to go there for a few months, well, for about a month. And I was looking at a synchrotron. And these synchrotrons are operated for 24 hours. So they were working me in shifts. So I was doing like 2 8-hour shifts at a time. And so that was pretty strenuous in itself. And in the end, they would have taken me out to eat, Chinese cuisine. And so I had the delight of experiencing all these sort of weird things, like eating chicken feet and things like that. Like various things, like cow stomach, cow tongue, all these various treats. The more worrying thing was when they didn't know what the translation was. So I was just eating unknown food, just for the hell of it. So that's about the most extreme story I have on that, I'm afraid.
I certainly couldn't eat chicken feet on no sleep. That's definitely.
Chicken feet was the worst, because you can tell they're chicken feet.
Although it's quite popular here, as I understand it.
Yeah.
Chicken feet, yeah. China. Okay. Sorry, carry on.
There's not a lot of meat on them, is what I can say.
Yeah, it sounds quite crunchy fun.
Yeah.
Okay, then I think the next furthest away is probably KZN. Mendy, would you like to introduce yourself? Are you there, Mendy?
They're laughing.
Oh, they have to put their microphone
Yeah,
on.
just put your microphone on, Mendy. Can you do it?
I'm chewing, sorry. Okay, hi everyone. My name is Mendy Shozi. I'm currently working at the CSIR in Durban. I did my undergrad in applied chemistry, then I did my honors in environmental science and my master's in environmental science. And I focused on assessing heavy metals in 2 river systems for both my honors and my master's. So I'm a freshwater person, so all your oceanography people, I have no idea what you're talking about. Embarrassing. I did a stint with diatoms at some point. So not that it was weird because I had to use a toothbrush to scrape them off rocks. So anyone was passing by just saw this person bent over. Probably my underwear was showing, who knows. And I was just scraping diatoms off. I mean, it's just black stuff, so I didn't even know if I was doing it right. So yeah, that's my story.
Thank you, Mendy. And then I think we have Pasander in Hateng.
Hello?
Pasander. Don't forget to unmute yourself.
Yeah. Hi, everybody. I'm Basanda Nundazi. I'm a master's candidate at Wits University. I'm an ecologist. And I think the weirdest moment in my life with research was when I had to chase thieves with my equipment worth over 40,000 rands. And luckily I caught them. And yeah, I think that was my talk. Thank you.
When you caught them, did you fight them? I mean, what did you do?
Well, I bumped them with a car, a few of them, and I had a gun with me as well, so you know what I did.
Okay, only in South Africa. Thank you, Sandra. I know I missed out in KZN, the famous and ever popular Fabian. Would you just like to reintroduce yourself? I know you were here last time. Don't forget to unmute your mic, Fabian. We can't hear you. There you are.
Can you hear me now?
Yes.
Yes. So it's Unizulu, Fabian from Unizulu. I started my career as a biochemist. I did honors in biochemistry as well, and then somewhere along the line, I disappeared and found myself in doing animal nutrition, where I managed to improve fiber digestion or fiber fermentation in ruminants. And I'm also looking at the impact of enteric gas production to the atmosphere as well. So how much gas is being produced by this animal and what does it do to the environment? That's a bit of what I'm doing. Now, in terms of what I've been doing in research, or the strangest thing I ever did when I came across when I was doing my research, I deal with wild animals where I collect fecal samples and try to extract microbes from them and test their activities. So one of my field animals was the wildebeest. So, and we went to the Tala game to collect fecal samples, and I had to spend, because the feces was supposed to be collected in situ, so it's like you have to physically see the animal. I dropped the feces for you to go and pick, so I had to wait for 4 hours waiting for these animals to give me a feces. 4 hours sitting in a van watching for 4 good hours, and get worse, I never even saw it when it happened, so I had to return home without a feces.
Nice one. Thank you. Cool. Thank you for that. I'd like to say a big thank you to all of the panel for joining us today. And let's get stuck into all of your questions. If you remember, at the last one of these meetings, we talked about all of the physical reasons why the Earth was habitable. And all that time ago, at the start of the course, we set up our really simple model, right? We looked at the planets and we saw that Mars was too cold and Venus was too hot, and we thought maybe Earth is the right distance from the Sun. We found out that if the Earth was just a ball of rock at a given distance from the Sun, it would actually be far too cold for life. So actually something more is needed in the model. So we added an atmosphere, and we talked about the greenhouse effect, and we found that that would make an Earth that was too hot. So we had to make the atmosphere move and add in an ocean, and then we looked at the paleo history, the long-term history of the planet. Now, this time, we're adding something really exciting to our model, and that's life. Okay? So we add biology and chemistry. And so these are going to be really, really interesting things that do stuff to our model. But firstly, they help make the planet habitable. They secondly make the mathematics incredibly more complicated. So in my first model, we could all do it on the back of an envelope. We could do the maths. As soon as you get into biology, you can't do that anymore. You can't model the behavior of all organisms all the time. You have to start working with conceptual models. But before we get on to any of that, I'm going to firstly tackle the talk, the origin of life. Now, normally, before we come on to your questions, I get a summary from one of our panelists about how this parameter helps make the planet habitable. Of course, with life and the origin of life, it's a bit obvious, right? I mean, by definition, habitable means that we have life. But nonetheless, I'm going to give Chris, can you just give us a 2-minute summary of what are the current scientific theories on how we think life arose on the planet to make it habitable by definition?
Okay, so I think as far as at least NASA is concerned, what they consider is when you look at the Earth, wherever you find water, you find life. So the idea is basically to sort of like try and see where there might be liquid water elsewhere, either in the solar system or on other exoplanets. And then that, by their definition, means it's a habitable planet or a habitable environment where you can have life.
We'll come on to that in a minute. Actually, one of the questions is going to come on to water and life, and obviously the book too. But what about on Earth? How do we think life started?
I mean, that's a really involved question. It's still being answered. As far as we've gone back in, you can go a certain amount of distance back in time, where you can trace, doing all the genetic tracing, you get these phylogenetic trees, where you can see how every organism is related And it all comes back to this thing called the last common ancestor, which is thought to have existed about 3.5 billion years ago. And from that, all life emerged and evolved from this sort of tree. On the other end of the scale, you can sort of say, if we start off with a planet with nothing on it, and we put all these sort of molecules on there, what sort of molecules can we form? And it turns out that things like amino acids, peptides, which make all the enzymes and do all the metabolism in your bodies, as well as things such as lipids, which make up all the cell walls, and even nucleobases, which make up the C, G, A, and T in your DNA, that all the transcription and all the genetic information is stored in. Those could actually be around. But we get so far, and then you basically can't figure out what happened. There's this big box of murky stuff that we don't know exactly what path life could have taken. So that's basically where we're trying to push things at the moment to see how, where life could have started. And the most prominent theory right now is this thing called the RNA world, which is at some point RNA took over, which is a molecule that is capable of both using genetic information, storing it, and also has some biological activity as well.
Yes, brilliant. Thank you very much for that, Chris. Of course, a competing theory to that is this one of panspermia, right, which is the idea that life may have actually arisen and come from outer space. So the first question we actually have is on that. It's from one of the students. Her name's Arushka, and she says, do you think viruses and bacteria, or organisms that could have entered Earth from other planets, are they highly evolved and adaptable because of the conditions they originated from? Does that sound likely?
Yeah. So panspermia is an interesting question. Are there any Star Trek fans in the audience? I have wondered why all of the characters in Star Trek look like humanoids, and the answer they provide actually is panspermia. At some point, there was some kind of precursor of DNA that was sent to all these alien worlds, and that's why they all have humanoid form. It's basically the kind of thing. So yeah, the idea of panspermia is just an organism or some kind of life precursor that is able to transport from one location to another within the solar system. And there are some people who think this is feasible, some who do not. A lot of people who don't really like this question because it's really dodging answering the question. For example, if you were to say, oh, sorry.
It's always the problem I have. I mean, really, that doesn't help you find the origin of life. I mean, it just puts the question back one. Sorry, carry on.
Right. So there's a lot of thoughts that actually, Mars, early on in the solar system, might have been a more favorable place than Earth for life to have originated. So it might have been warmer and wetter than the Earth. It's also further away, so it had less bombardment that might have wiped out Earth in the early times. So, but it still doesn't answer the question how life could have arose on Mars, and adds an extra question of how could life have got from Mars to Earth. And we know this can happen. Actually, whenever there's a large impact, a lot of material gets distributed all over the place. So to answer, is there any life on Mars? There should be, from Earth. We know around 65 million years ago, there was a very large impact where a lot of material would have actually come to the Martian surface. So if there are habitable places on Mars, it's possible that there could be life from Earth that was transported there. The issue with that is that actually it would have to have survived about a 6-month voyage or more through space, which is a vacuum. And vacuum, by definition, means there's not going to be any water, it's going to be really cold, and there's a really harsh radiation environment, so you can't really survive that very easily. Having said that, there are ways you can do it. And there are these molecules, I don't know if you saw the little origin of life slide that I did yet, but there's these little molecules called tardigrades, which also are called water bears, that happen to also look really cute, that are capable of surviving most of these conditions, such as radiation, vacuum, and also Bacillus subtilis, which are actually bacteria which are in your gut. And these actually, as part of their life cycle, when the conditions become unfavorable, they actually can go into these little spore stages, which are really able to withstand a lot of radiation and harsh conditions. And then when the conditions get better, they come out of these spores and they're able to propagate again. So there are some organisms that could do this and survive these conditions. And another way of doing it is just to bury yourself under a few layers of rock to shield yourself from that environment. So yeah, there are ways it's possible, but yeah, to me it is dodging that question.
And another one of the students asked, which is kind of related, he said, what do you make of the discovery of water on Mars? Does that necessarily therefore mean that there's life? I mean, you said that's NASA's opinion, right?
Right. So actually, I mean, I guess I should plug this here. The people responsible for that discovery were actually here at Georgia Tech. So a few things about that discovery. I don't know how much you guys know about it or not, but like the reason why it's an important discovery is the fact that it's the first sign of flowing liquid water on Mars. And that's not really true if you look at it in a lot of detail. What they actually found is evidence for a perchlorate water, and perchlorate is basically a salt. So we're talking about it as a sort of like a briny solution. And as you may know, when you add any kind of impurity to water, it has the effect of raising and lowering the water temperature, the temperature at which you can have liquid water. So for example, when it's snowing, the roads are snowing, they'll often go outside and put salt on it, so the water melts, becomes liquid water. The same principle is happening on Mars, where it's actually about 100 degrees Celsius below room temperature, and they have these perchlorate salts, which is able to lower the temperature at which you can have liquid water stable on the surface of Mars. So, having said that, it's not really the kind of like water that you can like just scoop up and drink. It would need to be a lot of treatment if you could actually get it. And the issue about sort of saying is it actually going to help us find areas which are habitable on Mars? There's actually a problem with that because as far as NASA is concerned, there's this thing called the Planetary Protection Act, which means if we actually have reason to believe that there could be life on Mars, we are not allowed to actually like bring anything there that could contaminate that region.
Okay.
Which is a bit of a problem. So it means we're not really allowed to go there.
So can the Russians do it, Neville says? Just the Americans who are stuck with that.
I don't know if that's worldwide or not. I don't know. That's a good question.
Okay, but next question actually kind of links in nicely. Sive asks, basically, maybe focusing on water is wrong. Is there any reason that we should pre-assume that life on other planets is in any way similar to life on this planet? Could it be completely different?
Yes.
In a word.
So can you repeat that question again? 1 second.
Is it wrong to pre-assume that life on other planets will be like life here? I mean, why should it need water? Why could it not be something completely different?
Yeah, and that is, I guess, like the biggest criticism of what NASA is doing is we are looking for life as we know it, and we could fail quite easily. For example, like we wouldn't even know if there were things like viruses if they didn't infect us directly, right? Like we've discovered them earlier than we would have done otherwise. And actually, a lot of the missions have failed because they've been looking specifically for certain things that we consider to be life, such as like the Viking mission that was sent to Mars. What they actually did is they assumed that if there was life on Mars, it would have a similar metabolism as ours and would respire CO2 the same way that we do. So they put down some nutrients that they thought that were labeled with a 14 carbon isotope, so this is a heavy carbon, and they waited around for a little bit and sort of they could see the evolvement of CO2 with this 14 carbon on there to see if it had evolved. And they got a positive detection, which meant maybe there's life on Mars. But then it turned out later that actually there's possibly ways you can get this happening anyway, just because there's radiation and there's these perchlorates, and those react with organic compounds to make CO2. So it depends what you're looking for. And yeah, there are absolutely many, many ways that there can be life not based on what we know, and will we be able to detect them? Maybe, maybe not. Okay. One of the most promising ways of doing that is called the Lego theory. So basically, if you're in any environment, there's a sort of like thermodynamic equilibrium that you can have. And if you find any molecules that shouldn't be there according to what you understand about the chemistry, and those are in higher abundance than they should be, it's possible that those are being created by life or used by life. So if you can find any of those anomalies, then that's maybe a way of finding it.
James Lovelock illustrates that, right, by saying if you take a box of air from the Earth and leave it isolated for a few years, it'll be completely different. Whereas if you take a box from Mars, it'll be exactly the same. It's that kind of principle.
Can I just ask a follow-up question?
Yeah.
One is that, would you agree that a lot of it depends on what your definition of life is? In other words, what's living, what's not living? Yes. One issue. And then just as a follow-up from an earlier point, is it true, in terms of life as we know it, that you can find water, which doesn't necessarily mean that there is life, but if you find life, it must mean that there is water?
Sure.
Briefly.
Sorry?
You want to comment, but it'll have to be briefly.
No, I mean that's true.
Okay. I want to bring things back to Earth now. Then, okay. So we've been out in space. We've looked at the RNA world theory of how life originated, and I think you touched on it. I mean, Becky has a question about how did that happen? How do we go from one molecule to multicellular life? And I think we've touched on RNA. Well, do you want to just elaborate a little bit? I mean, it's a huge story to tell in 1 or 2 minutes. But he says he can't get his head around it. How would you convince him?
Yeah, I mean that is a tough question. The only thing I can sort of say is when you look at outside of our solar system, or like outside of Earth, and what are the abundant molecules, we see that water is the most abundant solid state molecule. We know that the next most abundant molecule atoms are carbon, nitrogen, and oxygen. So the kind of like hydrocarbon-based life forms that we are doesn't seem like that unfeasible at all. We also know that things like amino acids, when they hit a hot mineral surface, they'll form peptides right away. We know that, for example, a lot of the meteorites contain a lot of things like amino acids, nuclear bases, and lipids. So it's really fairly convincing that you can form things like peptides that will have biological activity. You can form cell-like structures from those lipids that come together, like detergent soap bubbles kind of things. The big question, though, is like, yeah, the link to RNA and DNA is not set in stone, and that's where things could vary drastically.
Sure. It's difficult to imagine. The other thing you have to throw into the equation, right, is millions, in fact, billions of years. I mean, it's really difficult for the human mind to grasp how much can happen in that sheer volume of time.
Right.
So Devani asks, how can modern microbes inform ancient Earth ecosystems? So I think they're asking, what can we learn about ancient ecosystems from modern ones? Raissa, you want to say something on that? I've had enough of Chris.
Well, so the main idea is that we can't go and experiment on ancient microbes. The modern ones are what we have. And by understanding how they react to different conditions, we can try to figure out what they did back, how the conditions were in the past. The problem is we are assuming that things didn't change and that everything is the same. So modern microbes will react the same way ancient ones did, but it is the best we have. Maybe Chris wants to add something.
Chris, you want to comment there?
Yeah, I don't really have much to add. I was just sort of going to say that there are maybe some clues in the genetic code of some of these materials that can help trace back what genes they used to express that might be able to like give some clues as to what the ecosystems was like and something like that. But yeah, it's really a difficult thing to figure out as well.
Mike here, just to pick up on this microbacteria story. One area of possible where we could look for information is in hydrothermal vents, because these chemosynthetic bacteria are living in a very harsh, ancient environment that might have been somewhat similar to primitive or Earth's very, very early history, and the ability of these heat-tolerant bacteria can also give us a clue that links the past with the present.
Okay, Neville.
So I'm going to go off on a little tangent. You can weigh me in if you need to. And that's about oxygen and the role of oxygen in life, in the history of life. And as you might have been informed, or you might know and have learned, that when oxygen was produced in the atmosphere, it was very toxic to life at the time. And it took a long time until the oceans became oxidized and they all rusted, all the iron went out, and oxygen became part of a component of the atmosphere and stabilized ultimately. But if it wasn't for the fact that organisms could find a way to use oxygen as a means of neutralizing it, otherwise it's toxic, then we wouldn't have respiration. So it's really important to understand that microbes, as we see today, as you said, Raissa, microbes are everywhere. They're absolutely, in all environments you'll find them, even extreme environments. So we know that they have a very high turnover rate, they can evolve very quickly, so they have a good ability to respond. My point is that microbes have played a very important role at different junctures along the evolution of life in general. And one thing which a lot of people might not know is about mitochondria in the cell. So you all know you have mitochondria, right? And what are the mitochondria? You know they're there for parts of respiration, especially the parts of respiration that involve oxygen. And so the theory, and there's one other feature that I need to point out, mitochondria is the only other place in your cell, other than the nucleus, where you'll find DNA. So the question is, why does the mitochondrion have DNA of its own? And more interestingly, that DNA system in the mitochondria is a little bit different from that in the nucleus. And the answer is, the theory is, that in fact, they are endosymbiotic. At some point in the history of life, those organs, those organelles in your cell were in fact independent microbial organisms. And they became enveloped into metazoans, and they play the role of absorbing oxygen without oxygen to produce extra energy from respiration. But in fact, what it means is that we are actually mixed organisms. We have another organism living within us from a biological evolutionary point of view. That's to be explored another time, but I just wanted to point out that microbes really important in all sorts of ways to the evolution of life.
Perfect. Thanks, Neville. Just moving away from life and back to space, just quickly. Chris, one of the students asked, and it was Sive. Oh no, hang on, sorry, I've got it wrong.
I'll carry on talking if you want.
That's fine, thanks. Charlotte, sorry, I lost my place in the questions. It wants to know, how much must the Earth's orbit be shifted in order to kill off all life on Earth? Chris, you want to comment?
I can tell you what I looked up, which is the value between 0.7 to 1.5 AU. Apparently, is the realm of like the habitable zone.
The AU, that's astronomical units, right?
So 1 AU is how far Earth is, right? So if we got 25% closer to the sun or 50% further away, then probably, yeah.
All right.
Don't have much more to comment on that.
Who worked that out?
Probably someone like George.
Yeah. If you look it up, there's a lot of different estimates from different people. Like, there's how I don't know.
So I'm going to move on from the origins of life. Redani, do we have anything on social media so far?
No, not yet.
All right, guys, please do remember we need your questions. Tweet in or head in on Facebook. I'm going to move on. Oh, sorry.
Chris, I was just going to ask you those astronomical unit values that you gave. Where does the sort of Milankovitch cycle fit into that? You know, how far or how close is Earth relative to the Sun within those parameters that you've just given?
Oh, it's 1. It's defined as 1 AU.
But I mean, in terms of the Milankovitch cycles, right, the Earth does naturally move.
Oh no, the Earth has an eccentricity of like 0.1% or something like that. So it really doesn't. It's really pretty much at 1 AU the whole time.
Okay.
That's not more the angle of the axis rather than the actual movement of the Earth's orbit.
Well, it's the eccentricity.
Okay.
Okay.
As opposed to
I need to press.
The seasons are caused by the tilt more than the change in distance. Yeah.
All right. I need to press on. I'm going to move on to amazing water, and I will give a quick summary. So we've introduced life into our model, and then we take a little bit of a sidestep to look at the one comment that Chris made, that basically on Earth, we can find life almost anywhere. Right? Scientists used to think that life only formed in what's called the habitable zone. Not too hot, not too cold, not too salty, not too little radiation, not too much radiation. There's a guy called Dole, worked for NASA in the 1960s, came up with this and said you wouldn't find life outside of these reasonable bounds. And then it turns out that for the 1970s and 80s, scientists discovered a group of organisms called extremophiles. And these guys will live basically anywhere. They will live in temperatures of up to 120 degrees in hot geysers. They'll live below zero. They will live in extreme salt. They'll live with no salt. They'll live with, in fact, in a nuclear reactor. There was a radiation leak in a French nuclear reactor in the 80s because bacteria ate away one of the seals right inside the reactor. It's incredible the range of places that these organisms will live, but they will only find life where there's liquid water. And so we had a whole talk looking at why is it that liquid water is this so incredible, such important thing that it's the only apparent criteria for life. And I'm a chemist, as I said, and it all comes down to chemistry, so it's for me one of the most exciting talks. And what we discovered is that the incredible properties of water come down to two things. First, that it's a liquid. That's the less interesting bit. So we learned that life needs to pass on information from one generation to the next. And that if the medium that life was in was solid, then all the atoms are arranged in a rigorous grid, like this. And they never move. So if you want to pass on information from atom A to atom B, it would never happen, even though they're only 2 atoms apart. In a gas, the molecules are free-moving. They're flying around. They very rarely meet each other. So if you want to pass on information from atom A to atom B, the chances of them ever meeting is almost 0. So once again, life couldn't exist. But in a liquid, it's like Goldilocks. You know, in the story, she has a porridge which is too hot, and one which is too cold, and one which is just right. Liquid is just right. The molecules move, but they're kept close to one another. And this allows life to do one of its key things, to pass information, genetic information, from one generation to the next. So that's key. We needed a liquid. But then why water? Why not some other liquid? And this is where it becomes really cool in terms of the chemistry. And it's the chemistry of water that is all determined by this one small quirk of the molecule. The water molecule has an oxygen, which can be played by my head, and 2 hydrogens. And instead of being linear, it's bent. So the hydrogens go like this, and they vibrate like this or like this. So and they can turn and rotate. And it's that quirk in the chemistry that means water ends up with a charge distribution. One end is positive, one end is negative. And this allows it to stick together better, a thing called hydrogen bonding, but also to maintain heat better. And to stick together means that when you heat it, you have to put in more energy to make the molecules move. Heating is, after all, giving molecules energy. And so water ends up with a range of properties, from ice floating on water to a high specific heat capacity, to it being stable, to it being a liquid over a much greater range of temperatures than anything else, that make it the perfect medium for life. So water really truly is the most exceptional common compound that we have. And we didn't get many questions from you guys on water, but the ones we did were both eclectic and fantastic, so I'm just going to go into them in any order. The first one is from Ayama, and she asks, what makes water scarce on Earth when we know that 71% of the surface is covered in it? Mike?
Okay, I think you have to define what you mean by scarce, because you're quite right, 71% of the Earth is covered in water, but most of that's oceanic water, which is salty. So from a marine perspective, water isn't at all scarce. I think you're probably thinking of scarcity of fresh water on land systems, and certainly there are areas that are very arid and dry, where water is certainly scarce, and yet there are other parts of the land masses where rainfall is very high, and you wouldn't describe water as being scarce at all. So perhaps if I could just elaborate a little bit on that, you have essentially a hydrological cycle where as the Earth or as the oceans warm up, you get evaporation. That increases the amount of water vapor in the atmosphere. As that water vapor rises up into the cooler parts of the atmosphere, it condenses and falls out again as rainfall. But that distribution of rainfall is not uniform across the land masses. So in some areas you get very little rain, and in some areas you get a lot more rain. Now basically, with a high pressure system, you have descending air, and where you have descending air, it tends to be dry. and therefore arid. And in low pressure systems where you have ascending or rising air, you get that moist air rising, and you then get condensation and rainfall. So that's the basic answer that I can give you about the relative scarcity of water. And if I think of it a little bit further on in terms of climate change, it's quite unpredictable how this is going to affect the distribution of rainfall around the Earth. So, for example, in some parts of South Africa, for example, in the western areas, it's expected to get drier, whilst in the western areas, sorry, in the eastern areas of southern Africa, it's expected to get wetter. So with changing temperatures, the relative distribution of drought and rainfall is going to change quite a bit.
I'll put a controversial idea to you, Mike. I mean, your big point is there's loads of water, but not a lot of drinking water, and it's cycled, and that's great. I mean, it's really important. Water is also amazing because it's cycled, and we never run out of it. But lots of people come up and say, you know, okay, there's a problem with there's not enough drinking water, fresh water.
Right.
But I'd say, I mean, you just desalinize it. The technology is there. Absolutely. The problem is not a shortage of water, it's a shortage of energy. Because to desalinize it, you're going to have to burn fossil fuels and you're going to cause climate change.
Okay, I mean, there are a number of technologies now that don't necessarily need fossil fuels to desalinate water. So things like reverse osmosis can give you fresh drinking water without having to use fossil fuels. But yes, you're quite right. There's a distinction between what you might call potable or drinking water and other sources of water on land which are too polluted for either us or animals to use. So we need to actually take care of our water resources. And in future, if you ask the question, will we run out of water? The answer is probably no, but we need to recycle that water more effectively. Okay,
thank you, Mike. A related question, when we talked about the cycling of water, one of the big parts of that is rainfall. Obviously, it evaporates from the ocean and rains on the land. Lindelani asks, doesn't the rainfall, as it's raining, get contaminated by harmful particles found in the atmosphere?
Well, that's a very interesting question, and you might have heard of acid rain, and this is where excess sulfur dioxide that gets emitted into the atmosphere combines with water vapor in the atmosphere, and it falls back to Earth as low pH rainfall, and that can be a serious problem in terms of acidic rainfall, which has caused, well, actually the death of quite a few forests in the northern hemisphere in particular. But any particles that are in the atmosphere will certainly be incorporated into rain as it falls and bring whatever those particles are down to Earth with the water.
Nice one, thanks, Mike. So I also have one from Simonye, who's obviously on top of current events because they want to ask about hydraulic fracking, hydraulic fracturing, or as it's called, fracking. You might have seen on Facebook recently, I was advocating its merits, suggesting that it's a great idea because in the Eastern Cape we have a lot of unemployment and we can bring some great jobs there. But Simonye asks, how will fracking affect the water in South Africa? So I presume I'm going to bring KZ in on this. Mendy, do you want to tell us a little bit about that? Mendy Shozi, are you there?
Yes, I'm here. So Carl raised a great point there about the employment. So obviously fracking, which will happen in the Karoo, there's a great chance of employment for people that aren't employed. However, economically and in terms of the environment, not so good. I'll touch on the water just now. Economically, if I'm not mistaken, the shale gas in the Karoo Basin is about 4 kilometers deep, which is it's just deeper than most places in the rest of the world. So obviously trying to get to those parts to get the natural gas, that will take quite a lot of energy, first of all, and you know we have a crisis with our energy, and it will take a lot of money. So I'm not sure how it will help economically. And in terms of our water, it's quite a water expensive process to do fracking. And as Oyama noted, that we are quite water scarce, not only on Earth, but in South Africa. We have restrictions in KZN. And also, there's aquifers underground, groundwater as well. So there's a chance that you might contaminate these with methane gas or with any other chemicals that they use in the fracking process. But yeah, I'm not a very big fracking person, so if anyone else in the panel wants to elaborate, they can.
Can I jump in there a little bit? One of the big arguments with climate change is that we must limit CO2 emissions. So if you're going to get involved in fracking, you're adding to these CO2 emissions, but in fact, the IPCC pretty much states that we must leave fossil fuels in the ground and actually turn towards green energy.
But Beyond Longboard calculates that fracking creates about half the CO2 of coal or oil, so you're actually contributing to reducing CO2.
If you replace
shale gas.
Yeah. So the point there is there's a concept in fisheries called fishing down the food web, which simply means that the easy resources that are easy to get, you use them first. Then you have to go a bit deeper to get a few more. Then you have to go deeper. So the cost of extracting more and more of the resource costs more and more and more and more. So ultimately, it becomes an expensive exercise, besides the fact that we are still maintaining our addiction to oil. So I think that ultimately these are problems which we have to look at the cost and benefit of, and the judgment in the end is going to be subjective. It might be politically more important right now to employ more people, to give them jobs so that they can have decent lives, they can educate their children. That might be a more important priority than worrying about the long-term effects of CO2. On the other hand, we might be creating problems for our future generations, which would be avoidable now if we looked for alternative ways to produce energy. And that's the debate. And whether one is right or one is wrong is always a problem to decide. A lot depends on your perspective, your values, your political point of view. And so I don't think there's any real solution. I'm against fracking.
Well, I just want to pick up on what my colleague has just said. As individuals, you and I might not worry too much about climate change and global warming. You would certainly worry about the impacts of climate change for your children and your grandchildren. So therefore, you have to think. You have to think about them in the future, and decisions we make now, in terms of perhaps fracking for employment benefits. I don't think that outweighs the future consideration of CO2-driven climate change. But maybe I'm just giving you a personal perspective that doesn't stand up to scrutiny.
I have to just quickly qualify my statement. I'm pro-fracking, I'm also pro-employment. I must just point out that I'm sorry, I'm anti-fracking, but I'm also pro-employment. Meaning, I'm not saying that it's either fracking or jobs. That's not I don't think that's necessarily the point.
Well, I was going to pick up on employment. Well, fracking is going to give employment, but why are we not creating jobs in renewable energy? Because we could be employing people to build solar panels. We could be employing people to build wind turbines.
But the question is location. I mean, we took a field trip. Were you there in Pearson? No, but the point is, in towns like Pearson in the Eastern Cape, where we did a field trip, we talked to sociologists there. There's nothing. There's no road links. There's no factories. There's no. It makes no economic sense to build solar panels there because you can't ship them anyway. There's no port. There's nothing. The town is miserable. They have the highest rates of HIV and rape in the country. Nobody has anything to do. There's a whole load of shale gas under there that could provide jobs. We can also, it's not an either or, right? We can also do solar panels in Cape Town.
That's a fallacious argument, only in the sense that there's no industry there right now to extract that shale gas. So they have to bring an industry there.
Yeah.
They can bring any industry there.
No, but they wouldn't bring any industry there because there's no road links, there's nothing. They would bring a shale gas industry there because the resource is there. That's the only reason. Shell wouldn't locate any other plant there.
Shell destroyed Ogoni land in Nigeria.
They did, yeah, it was terrible.
So let's not play with that.
All right, I'm going to have to press on as fascinating as the discussion will be. So into our model now, we have a bare Earth. We decided that life originated and we decided that water is needed for life. But we're now going to start adding layers of complexity to the model, and as you saw in the lectures, we started by introducing one of the most interesting forms of life called plants. And I'm going to head over to Vasander and Hatain. Just very quickly, Vasander, we're running a bit behind, so just 2 minutes on why are plants important in a habitable planet, please?
Okay, thanks, Carl. That talk is an important talk because it's the talk that highlights to us that we need to have a habitable planet, but we have everything else, but without including life itself, we don't get that habitable planet. And everything that we have done in our model before that talk is basically modeling the temperature of Earth. And we add different characteristics of Earth, but talking about the temperature of Earth. And plants come in because they do a number of things in terms of changing the proportions of carbon dioxide to oxygen. And those proportions are important because there is a correlation between levels of carbon dioxide in the atmosphere and Earth's temperatures. So we touch on a number of things like the Bennett ion formations. I know there's a question that's coming on that. And that plants also assisted in the development of the ozone layer, and something that Neville touched on, the endogenesis, how cyanobacteria became part of other life forms. And we also touch on reproduction because reproduction is important when you talk about evolution. And there's also a question on evolution. Plants do evolve as well, but a big part of that involves reproduction.
Yes,
And yes.
Can I interrupt you and just...
Yes, no, it's fine.
The question touches on that early evolution of plants. Shivangu really basically just asked you to give a bit more detail on that. So can you just go into the early evolution? How did the first photosynthetic plants evolve, and how does that end up with all the plants we have today?
There are key features that these plants acquired. I'm not aware of the overall evolution, but I know that the key features are in one of my slides. There are key features that also pertain the reproduction of those plants. So the sophistication in how those plants became was mainly around how they reproduce or defend their reproductive organs or transform their reproductive organs to be more sophisticated to withstand the pressures that were put on them by Earth. I don't know if I answer your question or you'd like me to say more.
I can't speak for the students. I can't speak. I can't speak at all, but that sounds good.
Okay, but just to finalize, then we talk about photosynthesis, of course, because it is the main process that these plants get involved with in this whole story. And yeah, that's about it.
That's beautiful. Thanks, Vasander. Punzo asks, do you think in years to come there'll be enough oxygen for humans and animals? And I like this. On her questions for scientists, she ends it with "motivate your answer."
Yeah, I mean, very much on the lines of what Neville spoke about. If you consider oxygen in itself, it is also involved in the carbon dioxide molecule. So whether or not it will be there or not, that question is irrelevant. It will be there, but the question is, will it be available for plants? For animals to use? And that's a question. It depends on the proportions of carbon dioxide, and yeah, that's about it. I think it will be available, but the question is, will it be in amounts that are either accessible or not?
I was looking into this, Vasander, and I mean, basically, after photosynthesis evolved, which is about 2 billion years ago, right, the first photosynthesis, am I right? I mean, from then on, the amount of oxygen in the atmosphere has been very, very constant. And so, if it's been constant for the best part of 2 or 3 billion years, why would we expect it to start changing now?
But you should remember, Carl, that also in the beginning, carbon dioxide was very abundant in the atmosphere, in fact, on Earth. And it had not changed for a very long time. It was stable. But we know what caused it to change. So something in evolution might cause the change.
Okay.
It's interesting to me to know that you just said, Carl, that was it the proportion of oxygen has been stable for a very long time?
About 2 billion years, yeah.
Okay. Because I imagine that there's some chemical, and this maybe Mike can help us with, some chemical processes that create a sort of equilibrium, and there's an exchange and a flux of oxygen, which is either used and combined with other chemicals to take it out of the atmosphere, and then there's a new supply. So there's some stoichemistry, there's some processes that are happening that can change, and proportions of oxygen can change in the atmosphere. And that just reminded me to say that, of course, depending on what altitude you're at, then the amount of oxygen that's available varies. And so you might know that there are people that live in very high altitudes whose blood chemistry is different and adapted to oxygen concentrations in the air that they're breathing. And so I think it's an S-shaped curve, which is about the association of oxygen with hemoglobin. The hemoglobin curve is different. So they can do better, they can survive and be active at very high altitudes, whereas somebody who's not adapted goes up there, can't, for example. So all of this
is a relative bit to it.
Yes, I just think that it's important to know that while it might have been stable for 2 billion years, it doesn't mean it always will be, especially if the source of oxygen is affected. One more thing I want to just throw in is just to remind people that the production of oxygen which comes from plants are not only plants on land, but probably more so from plants in the ocean.
You're preempting the next question.
Yes.
I'll ask it anyway. Untutuzelo asks, does all the oxygen in the air come from trees? If not, where does it come from? Right?
Sorry. Well, I mean, Neville's answered that question. Phytoplankton.
Yes, Fabian.
I'm trying to say, with the question of oxygen, why would it reduce? What about the growing human population?
It's a very
oxygen is increasing as well.
Yeah, but the biggest.
A long time ago, we were less than how many billion? And today, how many are we?
But there used to be a lot of dinosaurs, and they're a lot bigger than humans.
But there were few.
But the largest contribution to the metabolism of oxygen and carbon dioxide on Earth is in microbes, not animals of our size.
There's a lot more of them, even in terms of biomass, right?
Yes.
We're very small.
Yeah.
Yes, that's not too stress.
But I mean, on that oxygen story, there's one interesting tiny little bit, and that is with burning of fossil fuel, you can actually measure the decrease in oxygen in the atmosphere as a result of burning fossil fuel. Okay. Although it's a very, very small amount, and you're not going to run out of oxygen anytime soon.
Can I ask you, Mike, is that reduction that you can measure a change in proportion of oxygen or an actual loss of oxygen, absolute loss? In other words, is it just because the relative ratio of the different components of the atmosphere are changing, or is oxygen actually getting less to that extent?
Whoa, I've been put on the spot a little bit because the way it's actually measured is relative to the concentration of nitrogen.
Yeah, I would assume that it would stay because Earth is a closed system, so there's no way for this oxygen to just disappear out of thin air. So it's basically the oxygen level being converted to something else, and it's staying within the whole system.
But a lot of it goes into rocks, right? So it can actually get out of the atmosphere.
Yeah. I'm talking about atmospheric oxygen, as in oxygen available for
yeah, so the atmosphere isn't a closed system.
So oxygen, yes, of course, can be made into carbon dioxide, all sorts of things that oxidizes. Yes, so it can be less available in the atmosphere. I imagine that if the source and the consumption of oxygen remain in equilibrium, more or less, the flux, in other words, then we're okay.
Yeah, but you can't. There is a measurable decline of oxygen in the atmosphere, but it's so tiny that it's almost imperceptible.
So what about this story of ozone layer depletion? What's the story about that then?
Ozone layer depletion.
What about the story of ozone layer depletion? Is that what you say?
Ozone layer is 3 oxygen. Am I making a mistake?
No, well, I mean, ozone is O3, right? But when you deplete it, you turn it into O2. So in terms of breathable oxygen, that's actually making more.
Just creates other problems.
Just creates other problems, yes. distinct.
By the way, just in case you think the ozone problem has been solved, it hasn't.
Oh, really?
It was just posted today. I saw something on
I remember the graph that the hole was getting bigger and bigger and bigger and then leveled off, and then it came up a little bit. That was a few years ago.
I'll have to look it up. I'll post it on.
Yeah, but I mean, okay.
Neville will post.
But,
He's promising.
But something for you, Carl. You're saying that stratospheric ozone gets converted into oxygen, but that's in the stratosphere, so that doesn't exactly make it available to us.
No, true. I mean, there's some mixing between the two, so it's stable. It will get there.
Yeah.
Okay, I have to move on. Very quick question, I hope, to Neville.
No such thing.
Both Tambani and Akorna asked basically the same question. So, is it fair to say that without any plants, there would be no life on the planet?
So my answer to that question, as I thought about it, was that if there's something that causes all of our plants to go extinct, then I'm quite sure it will cause us to go extinct for the same reason the plants do. But the short answer is, for human life, most probably yes. If there were no plants, there would be no humans. But that doesn't mean there won't be life. What's important is a source of primary production. That's what's important. And primary production, that depends on photosynthesis, depends on the sun. There are other sources of production. Mike mentioned it earlier, for example, in the hydrothermal vents, where production doesn't use the sun as a source. It uses heat from the Earth's core, and there's a hydrogen sulfide.
It's chemosynthesis.
It's chemosynthesis. So there are other ways of producing products, as in carbohydrates and things like that, which come from other sources. But we are dependent on plant material ultimately. My answer is, if we didn't have plants, we'd be gone.
Can I ask, is there a chance that we might actually evolve? Or
probably not quickly enough to catch up with that. I mean, we might be able to produce technology, might be able to produce something if we had the fuel for it, but that would be limited. Ultimately, through the sunlight is our source of energy through a biological system. So, I mean, if we could quickly invent some very rich people might say.
Yeah, it's just a thought experiment. If suddenly plants disappear, like how long would we survive with the food that we have?
I think the oxygen would be the problem first before the food.
Yeah.
I mean, we've got canned
How long
food.
would it, yeah.
Probably kill each other before.
Would you like to just quickly introduce yourself? Your off-screen and
just to lean in and say hello to I was hoping not to, but I'm Albert Moti from University of KwaZulu-Natal, and I'm enjoying the discussions. Yeah.
Thank you.
See the face.
Yes. You like to lean in?
Oh, only see my head.
There you are. Okay, excellent. Thank you, Professor. I want to move on to the next question. Letukatula asks, does soil erosion threaten the habitability of planet Earth? I'm going to start off with one of my controversial answers, which is absolutely not. Soil erosion is definitely a problem, and there's very much uncertainty as to how much soil we actually lose, because one of the big problems in quantifying this is that when soil is lost from one place, it probably ends up somewhere else. Although the net balance in the last 200 years is definitely negative. We have lost fertile soil. So soil erosion, you would have thought, is a problem. But in that time, productivity per square meter has gone up hundreds and hundreds of times. So we actually produce more. Soil erosion probably accounts for, they estimate in Northern Africa, a reduction of about 1 or 2%. But the amount that's gone up per square meter is more like 20 to 30%. So the overall has actually been an increase. The other thing to say is that if you're rich enough, you can actually put devices in to stop your soil from leaving. It's a problem of poverty at the end of the day. So my answer would be that it would affect some poor farmers in regional areas, but it's not likely to be the end of humans or to be ever a global problem. I don't know if Basander, our botanist, did you have anything to add to that? Did you hear it? I know you just had some connection issues.
Yeah, I heard that. I would just like to say that, you know, topsoil is very important. It doesn't have the same structure as the rest of the other parts of the soil profile. And if we lose topsoil, even if we have ample nutrients to feed to the soil, we can't give the plants that structure that topsoil has. So as much as what you're saying is true, our our quality of fertilizers, or what our fertilizers can do for our plants, has also been improving proportionally to the improvement in the production. So it doesn't necessarily mean that topsoil is useless, but it means that we have also developed quality or better performing fertilizers alongside our loss of topsoil.
Okay, nice one. Thank you, Basanda. I've also got another question for you, which is one of my favorite ones. It comes from Tamaka, who asks, what limits leaves from absorbing green light?
I'll just assume that I didn't see the person's name. I'll just assume that they are assuming that plants don't use green light. They don't respond. It's an electromagnetic spectrum. They don't respond to the frequency as well as they respond to other frequencies. Not that they don't absorb green light. So I don't know if I've answered the question or that person would be satisfied.
I don't really understand the question.
What limits the amount of green light they absorb?
Well, it's a matter of the wavelength that is absorbed by the plants and their selectivity. And I think the question is, why is it that they're selecting that wavelength between 400 and 700 instead of the green light? And to me, it's got to do with the preference by the photosynthetic processes. And again, I don't think we've done enough research to identify some plants that would prefer that area. I think that's an area that needs more research, because it is possible that there are plants that would prefer that area, but they are not the ones that we are using for the purposes of living on Earth as human beings.
The question I always put to the students is why aren't all plants black? I mean, surely if a plant would be black and absorb all of the spectrum, so it just evolves different pigments, right? So it evolves all, that would be a huge advantage. All plants should. Sorry?
So what's the answer?
I don't know. I'm waiting for someone to give me a good answer. Maybe just.
It's because they are green. That's why they aren't black.
That algae, marine algae, are classified as red, brown, and green algae because they do have different photosynthetic.
But why not black? A black plant would outcompete all the others.
Maybe they're too hot.
Yeah, that's been posed as a possibility. Okay, and then I've got to retort to that. Why don't we get more darker plants as you go further north? You would expect, if that was the reason, that by the Arctic tundra all the plants would be dark, and by the tropics they would all be light, but they're not.
But Carl, they do.
Yeah, and we've lost Basanda.
I think he was going to say they do get darker.
Do they?
Well, I don't know.
It's a fascinating question. I've always wanted. Basanda, are you back? Basanda, we just lost you there. Okay. I'm going to have to push on, I'm afraid. We are pressed for time. Redani, do we have anything on social media?
We had a question regarding amazing water.
Okay.
Comes straight from the famous Pumulani Mangete. You know. So he's saying, as my knowledge is concerned, I know that when we're doing water allocations or budget in South Africa and in Africa as a whole, we reserve some for aquatic ecosystem, some for environmental flows, and lastly for humans as their basic human need. So do we say that water scarcity, because it is affecting humans, or because, I think you want to say we're so conscious about biology or aquatic, if it was not affecting us, we will be saying the same thing, or?
So it's basically saying, are we only worried about water because it affects us?
Yes.
I mean, I would say yes.
Well, I think there's another way of thinking about that, and that is, for crop production, water is vital. So.
But that's us again.
Well, it's us once removed.
No, for natural systems on which we depend, which is okay, water is important.
Yeah.
Can I just say something quickly? And take it first time. We're experiencing a drought in South Africa. It's important to note that. I'm surprised nobody's asked that specific question. We have an El Nino, which might or might not be driving this particular drought. But today on the radio I heard a conversation about it. And one of the issues we've got is the management of our potable water. Not just the management of the supply, but when it's used, it comes out of sewage, and the treatment of sewage in a drought situation is really critical in keeping water still potable. So rivers get contaminated by sewage. When they're flowing fine, it's no real problem. When the rivers are down, it is a problem. And there's a looming issue there for the country. So it's not just the scarcity of water, it's the quality of the water.
Okay. Anything else, Redani?
I'm not kidding, John. She's not quite sure, but she's saying fracking can also induce earthquakes. That's a question.
Yeah, that's true.
I think so, just not sure.
Mendy, do you have any comment on that? I think there is some research, right, linking fracking to earthquakes. Are you there, Miss Shozi?
She looks surprised.
Mendy Shozi.
Hello.
Hi, did you hear the question?
No.
So one of the students, who was it?
Anna
wrote in asking if there's a link between fracking and earthquakes. I said I thought there was some. Do you know anything about it?
No, never seen anything on that. Would it be mining for us?
Well, yes, mining as well. I mean, I think fracking, the risks are very similar to mining at the end of the day. Anyone want to say anything before I move on?
Just to say, I think there has been in the US, since they've been doing a lot of fracking, they have noticed about 1,000-fold increase in earthquakes or something like that.
Oh, wow.
In the areas where the fracking has been occurring. So I think that is pretty established.
Luckily, though, once again, there's nothing in the Eastern Cape to be demolished by an earthquake.
Chris, since you seem to be on top of the fracking story, what's the issue about its effect on water quality?
Yeah, I mean, there's also been some reports that it's contaminated water supplies in certain areas. I don't know how true that is or not. It's always difficult. A lot of the fracking companies say there is no issue, but some people have, been pouring out glasses of brown water. I don't know how true or not that is, though. I can't really substantiate. But on the plus side, the reason why the gas prices in the US are so low right now is because of fracking. Basically, it's about $2 a gallon right now, whereas it was up to about $5 a gallon before fracking.
I mean,
so there's a good and a bad side,
I mean, my interesting thought about that is if gas prices are so low, then the incentive to switch towards green energy can't be very high.
That's why they're fracking.
Sorry, I lost the sound there a little bit. Sorry. Could you maybe repeat that?
What I was saying is, if gas prices are so low in the US, has this had a negative effect on the development of green energy, solar and wind?
It's hard to say. I don't really know. I know that there has been in certain states a lot more of a push towards solar energy, such as California. But in general, I don't think so. I mean, I think overall people have been it's been a mixed response to the fracking. There's a good side and a bad side. And
the next. Sorry.
Another thing that I've heard about is that they don't want to go and exploit oil in places where it's a lot more expensive. So with deep ecosystems or in the Arctic, it might not be cost effective when you can get much cheaper gas from fracking. So then in that sense, it helps to protect some ecosystems. Is that?
Hey, Raissa, thank you.
I mean, but I'm not saying it's good. I'm just saying with all of its conflicts.
Okay, in terms of the sustainable energy side of things, we're going to be talking about that in the next discussion. So if your point's on that, we're going to have Teboho and Java from UCT, who's a brilliant planeteer and also a specialist in wind energy, so he'll talk to that. Neville, very quickly.
All I want to say is that the whole issue about the cost of oil, what's motivating fracking, where oil comes from, who's buying oil from who fixes the price of oil, the whole OPEC geopolitical issue, it's all highly politicized and strategic rather than purely economic and environmental. So it's much, much more complex than it might first appear. And so cheap oil in America from America is what America wants.
Yeah. Who doesn't? Yes. Redani, is there anything else?
No, so far.
Okay, that doesn't get you off the hook because they're going to move on to biodiversity and food webs now. So when we're coming to our model, we've now introduced plants. So we had a static ball of rock, we had an atmosphere, an ocean, etc. We've got life, we've got plants. Would a planet be habitable with just one species of plant? In the talk biodiversity, we find out not. I'm going to ask you to give a summary, Redani, but also to answer the first two questions in your summary, which is Shozi asks, why is biodiversity important? So I think that could come into your summary. And Afikile asks, why does biodiversity vary in different parts of the world?
All right, thanks, Carl. The interconnectivity of species through food webs and food chain, they are, I would say, the interconnectivity between food chain and food web, they work hand in hand with the stability of the ecosystem. So I would say that biodiversity is an important part of ecosystem services that are essential for the lively or that are essential to fulfill human needs as well as those of all life on Earth. So amongst those ecosystem services that I'm talking about, we're talking about the maintenance of ecological cycle, thus providing us with clean water, and also we talk about for example, wetlands. They help in cleaning our river systems as well as absorbing chemical pollutants. Some of the services or free services that we get from the ecosystem, we find that biodiversity helps in maintaining atmospheric quality. For example, it has been mentioned by Vasanda about the issue of we get oxygen from plants. And the versatile biodiversity also helps in controlling diseases as well as playing a role or a crucial role in pollination. So, lastly, in the question of why biodiversity varies in parts of the Earth or in different parts of the Earth, there are so many studies that have been undertaken, and it has been concluded that biodiversity decreases when we move away from the equator. So the equatorial areas experience or they don't experience major changes or seasonal changes in sunlight. So that's why you realize that conditions are excellent for abundant growth of animals and plants. That's when we find most of the world's rainforests are found in that particular area. And you find that forests grow quickly, and there are many layers. We also find different niches that provide habitats for animals. So when you move to the poles, there's no such different because normally it's cold throughout the year, and most of the plants and animals that are found in that particular area are adapted to that particular harsh conditions. But between the poles and the equator, we find that areas or we find that there are varying sunlight as well as rainfall amounts. So the those particular areas are diverse or are less diverse compared to rainforest, and more diverse compared to the poles.
I remember seeing that the scientists used to think, right, that the type of ecosystem that you've got was entirely dependent on the climate. And there was some famous graph where they drew temperature and rainfall, and then you can divide it up. But that no longer holds. Is that right?
I've learned.
Yeah.
Anyone? Cassandra, do you know this? Ah, he's gone just as I asked him a question. Okay, I'll leave it. I'll leave it. Okay, I'm going to go to more of the students' questions. I'm going to go to Deirdre's, who asks, what's the role of the oceans in biodiversity? And I'll add to that, Mike, as Redani was asking there, why different oceans have different levels of biodiversity?
That's an excellent question. And just thinking from the marine environment around South Africa, just as a quick refresher, on the west coast, you have the cold Benguela upwelling system that has low diversity but very high biomass of a few species like anchovy, pilchard, and hake. Meanwhile, on the east coast, which is dominated by the nutrient-poor Agulhas current, there's very high species diversity, but not much biomass of any particular species. So this difference in biodiversity has something to do with the nutrient supply and the emergence of either a lot of different animals occupying a lot of different niches, or a few animals that become dominant in perhaps one or two or three dominant niches. Does that answer the question?
Yeah, very nice.
What are dead zones in the ocean, Mike?
Well, dead zones in the ocean, as we understand them, I think, Raissa, is where you have oxygen depletion due to biological activity, and that oxygen depletion causes...
Because there's so much biomass and gets degraded, that uses oxygen. Then there's oxygen, well, there's no more oxygen left, nothing else can live.
So it kills everything in that area?
Well, it kills everything except microbes that can live without oxygen.
Yeah,
I see.
yeah.
So,
I mean, that comment doesn't, to me, remove the argument that biodiversity is still linked to environment, to climate.
Well, you see, I can't speak from a terrestrial perspective because I'm an oceanographer. When I'm sitting on a ship 20 miles out to sea, land looks like a little thin line in the distant horizon.
I'm confident, I haven't heard any other alternative theories, that climate is a very important driver of biodiversity.
Well, I'm getting this from Guy. Guy gave a talk at a conference where he showed the graph and then laid into it and disproved it. But it's maybe focusing on the exceptions. It still works as a rule. Sorry, Raissa.
No, I was going to add, I mean, the reason we see shifts in population moving with climate change, so that's also, I would think that would add to theory or support that there's links in biodiversity and climate.
Actually, that's reminded me, because you said the word Guy, I know what he's referring to. For example, it's not always mediated only by climate.
Yes.
There are other processes.
Yeah.
And one of those is fire.
Yes.
On land. So fire is very important. So two things. One is that if it weren't for fire, there would be no grasslands, because the fire burns the bush, the grass grows back, the fire burns the grass grows back. And so effectively the grasslands of the savannas, Africa, have developed and evolved because of fire. If it wasn't for fire, it wouldn't be savanna. So then the climate would be directly influencing how it grows. So in other words, fire keeps things, mediates things. Similarly, now, what we're seeing is increased carbon dioxide acting like fertilizer. So we're seeing more bush encroachment where there was savanna. So we're seeing a change happening again. So carbon dioxide is mediating the climate signal, and so is fire.
Okay, Mike, quickly.
Neville,
Yes.
yeah, there's a flaw in the argument that increased CO2 gives you necessarily increased
Productivity, plant
productivity or bushes, because it depends on what the limiting nutrient is. So if nitrogen is limiting, you can increase the amount of CO2, but you won't increase plant biomass. But you're right that bush encroachment is attributable to increased levels of CO2 and fire, but also the absence of mega herbivores comes into the story as well.
Okay, I'm going to move on because we're a bit pressed for time.
We're enjoying ourselves.
Yeah, no, it's great. But I'm going to really enjoy this one.
Enjoy the chips.
Silangile asks, basically I'm going to summarize the question, is that in a world that's driven by money, does conserving biodiversity have a utilitarian value? And I just want to clarify, utilitarianism is the idea that the best decision can be made by just finding out how something affects humans, all humans, finding out how happy it makes all humans, adding that up and taking the average. So utilitarianism would say in any decision, you have to make the one that will make the most people happy most of the time. So in that framework, does conserving biodiversity have a role? Will it be utilitarian or not?
Well, the short answer is yes. And mainly because of what Redani was saying, that we depend on the system as a whole for it to remain productive and for it to remain to provide us with ecosystem goods and services. And so by not conserving, first that's the utilitarian approach, which I'll develop in a minute if necessary. But there's something beyond utilitarian considerations, and that is the ethical considerations as well. You know, what's important to life is just human life. If human life existed in isolation of the natural environment in which we live, is that life? Is that good enough life? So, just we can exemplify this with the issue of the rhino. The rhino, of what value is the rhino to humans? Well, the only good value is that you can sell the horn and make a hell of a lot of money. So maybe it's worth farming it.
Yeah, but actually, I'll go back to my previous comment. Rhino are one of these mega herbivores that controlled bush encroachment. So, yeah, I mean, you can argue around this for
Indeed.
all ages.
Yeah. To make my point, I want to use a fisheries example of that. It's just where I come from. Okay. So, in the beginning of fisheries management, well, there was none. So basically, you went out and caught as many fish as you liked. And very quickly, we learned that if we don't manage how many fish we catch, we're going to basically wipe out the population, and it will be economically extinct, if not biologically extinct. It means we can't. It's not worth catching them. So we started to manage species, one species at a time. But then we quickly realized we can't manage just one species, because if we don't manage what that eats or what eats it, then we're going to lose the system, and the system won't sustain that fishery. So then we move to something called the ecosystem approach to fisheries, to try and understand fisheries as a whole system. And that involves not just the food that it eats, but it's the food that the food eats, and the food that the food that the food eats, and sometimes that's plankton. What produces plankton, or what promotes the production of plankton? So now we're looking at the abiotic factors. So now we're going to understand the system in terms of all of the physics, and the biological response, and the food chain, and the whole ecosystem. Even organisms we can't eat are important to those that we do eat. So that's an example of fisheries, and including humans, as it happens, because humans catch fish, so therefore they cause mortality. Similarly, with the whole environment, terrestrial environment, if you like, everything depends on everything else. And so, as a mechanism of preserving the productivity of the goods and services as we know them, and as we are dependent on them, we should be conservative. However, we have the option of taking the risk of not being conservative, but that means we have to engineer our environment, and engineer our productivity and our goods and services. And those are the options we have to choose.
Thank you, Neville. I'm going to move on, and Ntando asks, what are the main threats to biodiversity? Redani, can you give us a quick summary?
There are quite a number of, I would say that there are a wide variety of threats, but I'll just give the main ones that are well researched. We've got the habitat loss and degradation. They say this particular effect affects 86%, according to IUCN. This particular effect affects 86% of bird species. just over 87% of mammals, and also about 90% of amphibians. We also have the second threat, or the second factor, which is over-exploitation of natural resources. Here we talk about the issue of hunting as well as overfishing. We also have introduction of invasive alien species. South Africa, especially the South African National Biodiversity Institute, they are embarking on in a project of eradicating some of the alien invasive plants. Back in the days, I still remember there was also the Working for Water, where they were eradicating Lantana Camara. So there's also the issue of pollution and diseases. Another threat is human-induced climate change. They say climate change is affecting the migratory patterns of species, as well as contributing to what we call coral bleaching.
Okay, nice one. Thank you, Rendani. I'm going to summarise the next three questions in one because they all just link to that. And that's the Viwe, Nasipo, and Benedicta all basically ask, okay, so those are threats to biodiversity. What can be done about it? I'm going to give Fabian a go first, if you want to, Fabian. Fabian!
You guys hear me now?
Yes, we can hear you now.
I would like to first express my sincere gratitude for Prof. Modi joining us online. I'm quite delighted to hear that he's around. Then going back to the question, when I look at what the student asked, the question was not very simple. It was very complex. If I was going to look, because he was asking what can we do about the human population to reduce the extinction crisis. Now the human population, was the student trying to tell us about the variety or the influence of human to that, and so on and so forth. So when I look at that, I said, no, I'll assume that the question was simply talking about extinction of species on Earth. Okay. So when I looked at that, I'm saying, what does this student then mean by extinction crisis? Does that student understand, is it a disappearance or the extinction crisis? Because we also have radiation, so I assume that it was extinction of life because we're talking about habitable planet here. So they when I pulled that, and I did quite a bit of looking around and say, oh my word. So then I realized that we have up to 2/3 species on Earth disappearing, that have disappeared, and the stat that I saw, it's alarming. It was like, I'm not sure if anyone believes what I'm saying, but it was like one species disappearing a day. So it was really a very tricky one. So when I looked at that, and they was asking, what is the main cause of this disappearance or extinction of species on Earth? And most people, they said there was no one point that could be really pinpoint that this is this is the main cause of extinction of species. And from that point of view, we then say all these problems are interlinked. There is no specific one that we could put. But when we started, so when I looked around again and I saw that most people looked at the growing human population, they pinpoint that as one of the main reasons that is on the focal point of species extinction. Because when we then look at that, we start looking what are they doing that influences disappearance. We had deforestation. We had food chain where they hunt some of these things, they hunt some of these animals for food and so on. Like for example, the chimpanzee or the baboon in Cameroon, that species, their numbers are greatly disappearing because people, human beings, then tend to them as a source of income, irrespective of all the ban that has been put together, and they are aware that if you caught hunting this animal, you may be jailed for some time, but because of the economic crisis, this would always stay there. Okay, and things like that. And there are even war-torn countries when people throw bombs all around in particular places. This this species get extinct. You can get difficult situation. The growing human population also is causing migration. People move into places, into habitats where different species were living, and as human beings move to those places, then they further pushed or displaced these microbes or animals into different, to now start looking for different habitats which they are not adapted to. And by so doing, they then become vulnerable to other predators or other microbes that could then eat them as parasites as well. So with all of this put together, we see that there is these animals or these species will continue to disappear or being extinct if the knowledge, if people are not sensitized enough of the dangers of these animals decreasing or disappearing. Now, if we were able to know, then our people are going to know that, hey, come on, these species are endangered, we have to take care of them, and so people will start looking for alternative sources. People will start making sure they create habitats for species that are in danger of being extinct, and so on and so forth. From that point, I think that's how far I could go. There's a whole novel if I were to talk about that. There's just so many points, but with time, I'm not sure I could go on and on.
Thank you, Fabian. Basanda, do you have 1 or 2 words to add on what we can do to better conserve species?
No, thank you, Carl. Just that we must always know that education will play a big part. That's all.
Nice, I like that. Was 1 or 2 words. That's absolutely perfect. Thank you. And Mendani, you have anything to add?
I mean, it's more on the very same page with Basanda, but I mean, considering the biodiversity components is the way to go, and also giving priority to those components that require agent protection.
And I just add something. You see, the threat is not only biodiversity, it's also genetic diversity.
Yeah.
Because within a particular species, there is a wide range of genetic diversity. I think one of the inadvertent problems that we've created as humans is that while there are thousands of species that we can actually use for whatever reason, particularly for food, we've actually reduced the number of species that we rely upon to only a few. As a consequence of that, large areas of land, for example, for agriculture, are occupied by a handful of crops. And that has reduced the genetic diversity. And if a particular crop, for example, has got a particular problem associated with the environment, then that makes the problem worse.
So we just have to genetically modify them.
Yeah, we'll come to that.
But we need to have some genes.
We had some aliens earlier, and when we were talking about outer space, and I want to bring back to aliens, but actually on this planet. And Wako says that I've witnessed the deforestation of invasive plants, but don't they also deserve a place in the environment? I rhetorically put it out to the panel. I mean, every species is an invasive species if you go back far enough in history. Yes. What's the point?
I will give you a rhetorical answer and leave all the eucalyptus trees in Australia.
I have an answer, and the answer really comes down to what we define as important to us. So, and how quickly we can cope with change, and how quickly we can adapt to change. This is related to what you were asking earlier. Yeah, you referred to this earlier. So it's the speed of change and what we want. So, for example, inherently we are conservative. People are conservative inherently. Our values are to keep things the way we're used to them being. That's what we do. So, and we have evolved in a particular set, a particular regime of ecosystem dynamics and a particular regime of ecosystem goods and services. That's how our systems and our lives and our understanding of the world is developed. So, if we change that, we have to adapt to that change. Otherwise, we can't survive. That doesn't mean that alien invasives are necessarily a bad thing. If we wanted to keep things exactly as they've always been and functioning exactly as the way we want, then they are a bad thing. aside from the fact that yes, you know, most of the fruit that we grow in this country, and even the staples we grow in this country, are all alien species, actually, pretty much. I don't think there's anything endemic that we eat here. But my point simply is, if natural systems, if we want to keep them the way we know them, then we have to be conservative, and we have to try to conserve them. If that's not important, then that's a value decision. It's a value decision. Then we can let them change and just adapt accordingly.
I think one of the issues about invasive aliens is that they've invaded without their natural predators. So they can invade rapidly into areas that you might not want them to invade simply because the natural controls in their native countries don't exist here. But just to pick up on your point on an invasive alien that's been useful, is the Mediterranean mussel that has been introduced by ships into the West Coast region. And now the entire aquaculture industry for mussels is based on what historically was an invasive alien mussel. And it's now dominated the coastline completely. And you accept it as a natural part of the fauna now.
This is true of the wine industry, is it not?
That was actually good.
One of the really important things about Habitable Planet is we do like to persuade students to ask those questions about science that they've always wondered about. And so this one, it's off on a tangent a little bit, but it's the kind of question that we like to encourage, and we have a geneticist with us, so I'm going to put it to Godfrey. Noabisa asks, how can it be that an albino child can be born to two parents who are not?
Well, from a genetics point of view, so being an albino is actually not really a disease. It's just some genes are turned on, some are turned off. If you turn off a gene of melanin, well, you're not going to produce melanin. So during mating, then fertilization, some genes tend not to be turned on as they should. And then as a result, the offspring has that off gene for melanin, and then hence we call it albinos.
But if their parents are both non-albinos, how can they get an off gene?
You see, the thing is, with genes, we're not fixed, so everything changes all the time. The environment changes everything. So during the mating season, we even things. When people, when two people, male, female, make a child, what happens is that there's shifting of genes, and during that process of shifting of genes, you tend to have some mutations going in there. It can be environmental factors, it can be multiple kind of factors. But once that happens, certain genes tend to turn off. Some are just completely eradicated, hence you get people who have Down syndrome and other things. So, but the albino issue is just that one gene was being turned off, which is the gene for melanin production. Therefore, you will not have that pigment which other people will have.
Is this the same thing as dominant and recessive genes?
It's kind of like dominant and recessive genes. So you will have more for recessive gene, not necessarily recessive gene. So one of the dominant genes for melanin production gets then cut down, and you don't have that gene expressed. Therefore, you have that.
Okay.
Can I throw in just a slight further tangent, of course, and that is that the study of disease and inherited disease is quite fascinating. And so some of you might have heard of a disease called Huntington's disease. It's a terrible disease. The problem with Huntington's disease, it's a recessive gene, so that means that you have to inherit the gene from both parents to have the disease. If you only have one from one parent and not from the other, then you won't have the disease, but you'll be a carrier. Okay. But people that suffer from the gene, you think it's a lethal disease, a terrible disease, so it kills you. So how does the gene get passed on to the next generation? And the answer is the disease only manifests at 35 years of age. Late onset. So people are really reproduced, passed on the gene. It's very fascinating. There are many, many interesting examples like that.
Thanks, Neville. Yeah. All right, I'm going to have to move on to our final section, which is we've brought in plants, we've brought in biodiversity. The next bit we looked at was what's called biogeochemical cycles and feedbacks, how life mediates the passage of nutrients through the ecosystems. And I'm going to ask Raissa to just give a quick summary of how that helps make the planet habitable.
Well, Carl already said what I was going to say first, is that what is biogeochemistry? So it's the processes through which chemical elements and compounds are used and cycle them home. And why is it important? And we've mentioned this throughout the course of the discussion. It contributes to regulating the climate. So, for example, phytoplankton in the ocean take up carbon, and that helps to control the amount of CO2 in the atmosphere. The second thing is what Neville mentioned is they have a base of biochemistry helps to provide food. So we can't eat inorganic chemicals, but plants can use them. And then if you're like me, a vegetarian, you eat the plants, or if most other people, you will eat the cow. Or if you eat fish, what do fish eat? They eat zooplankton. What do zooplankton eat? They eat phytoplankton. And phytoplankton are the ones that use the chemicals. Biogeochemistry also helps with maintenance of habitat by controlling, say, the pH of seawater. Then you have the coral reefs that can be there. You have the mangroves and all of the forests. All of these at the base depend on chemicals that get used, and we also use them.
Nice one. Thank you, Raissa. I'm going to put the first question to you, which is from Ombuso. They want to ask, what effect do phytoplankton have on greenhouse gases in the atmosphere?
Well, we'll assume here that by greenhouse gases we mean carbon dioxide, because phytoplankton, through all sorts of processes in the marine environment, you can release and produce or take up other greenhouse gases like N2O, ethane that cannot be produced. But in terms of carbon dioxide, if there was no phytoplankton, the carbon dioxide would increase by about 50%.
You're the expert, Raissa.
Well, Mike has got a lot more experience than me.
Yeah, but my wisdom is on the wall.
So both Benedicta and Flora want to ask about geoengineering, and then specifically linked to the phytoplankton, this idea of ion fertilization. Mike, can you give us a quick synopsis? Ion fertilization, what is it? Does it work?
Okay, the basis of this is it really comes down to the Southern Ocean. The Southern Ocean has the world's largest unused reservoir of nitrate. And nitrate is an essential nitrogenous compound or inorganic nutrient phytoplankton use. And the basic argument is that the phytoplankton in the Southern Ocean are not able to use that nitrate because there's an enzyme that allows them to use nitrate that contains iron. But the Southern Ocean has so little iron in it that the phytoplankton can't use the nitrate. So the argument is, or was, that if we added iron to the Southern Ocean, could we in fact then geoengineer phytoplankton growth or increase phytoplankton growth in the Southern Ocean and therefore take up more carbon dioxide from the atmosphere in the way that Raissa has suggested? The bottom line is that there's been about 12 international experiments, of which South Africa has been part of one, where we have looked at iron addition experiments in the Southern Ocean. They do increase the amount of phytoplankton growth, but the bottom line and the consensus now is that it would be a bad idea to fertilize the Southern Oceans with iron because you actually create other problems that are more serious, notably ocean acidification, because if you draw more CO2 into the ocean by fertilizing the ocean, you lower the pH, and that's what's known as ocean acidification, and that problem is more severe than the benefit you would get from fertilizing the ocean.
Okay, that's nice. I mean, I want to very, very quickly just delve a little bit into geoengineering because it's a great topic. And Mendy, I'm warning you, I'm going to come to you on this because I think you'll have an opinion. The great thing, the really interesting dynamic on geoengineering, aside from just iron fertilization, which as Mike points out maybe doesn't work, is that there was a really interesting paper by an economist called Nordhaus in the early 2000s where he used a model called DICE, the Dynamic Integrated Climate and Economics Model. And what he showed was that if we stop burning fossil fuels and don't do geoengineering, by the end of the century, the people living in slums and townships today will probably be not much better off in the end of the century, in 2100. If we burn fossil fuels, then the effects of climate change will mean that the people living in townships, etc., will not be much better off. A little bit better, actually, he reckons, than none at all. But if we burn fossil fuels and find some way to geoengineer, they'll all be living at Western living standards or above. So it makes a huge difference to the world's poor if we can make this work. But, as Flora points out in the second part of her question, it could have disastrous effects. And I think, Mendy, you wanted to say something on that.
Oh gosh.
That wasn't the
engineering. Pardon?
That wasn't the response I expected.
Because I'm listening to your explanation and then suddenly it's like I had something to say. No, I was reading up on it, and when I did my research, when I did biogeochemical feedbacks, I thought geoengineering was like this wonderful thing. Like you build, you put up machines that can suck up CO2 and all that stuff. But then I was reading up on what happens to farmers in the northwest when these planes that do those chemical trails, those chemtrails, and those pseudo clouds, that is actually not working out well for them, because now that interferes with the natural cloud formation. And those clouds, they just dissipate as soon as the plane has left. So all they're left now with is dry and dusty weather. There's not a lot of rain. They hardly see blue skies. So I don't know. I'm starting to rethink it, because there's not quite a lot about geoengineering, even in legislation. So I don't know.
The other problem is there's so much uncertainty.
Absolutely.
We do a lot of experiments. We go try to put iron in the Southern Ocean. What happens? And different things happen at different times. So it's not only depend. If we just go and throw iron in, it's not always going to give the same response. The other geoengineering idea is to go and put in clouds, make more clouds, and it reflects more sunlight. But that's not solving the problem of ocean acidification that Mike mentioned. If we're still producing carbon dioxide, we will still have ocean acidification, which is a big problem. And then also we don't know much about the albedo. So the albedo is how much light, how much sunlight is being reflected. We don't know that value. We don't actually know that value properly. So now if we're going to change it, do we know what we're messing with?
There's all sorts of other, I'll very quickly, moral questions, like, you know, who decides that we should do it? Because it will affect the whole globe. And what happens if it does solve the problem for 90% of the globe, but actually turns Canada into an Arctic wasteland? Who compensates Canada? Who?
Yeah. I mean, there is one geoengineering option that's, I suppose, not strictly geoengineering, but carbon capture and storage. And this approach involves the idea of capturing carbon dioxide from the atmosphere, perhaps from factories that are producing CO2, capturing it chemically, and then pumping the captured carbon dioxide down into disused coal mine shafts, disused oil wells, deep underground aquifers, all in geologically stable regions. And in fact, that is being done in an oil field in the North Sea, where 1 million tons of CO2 are buried at a depth of over 1 kilometer every year. And that is a process that South Africa is looking at in terms of capturing and storing carbon dioxide. But it does, as Carl says, have a lot of political ramifications that we haven't really addressed properly yet.
And costly. Costs.
Yeah.
So one objection I heard to this is that we don't, how do we know that there's not going to be something at some point in the future that's going to break?
So this is the whole fundamental issue about conservation, as far as I understand it, is that we must decide, either we want to keep everything the same and keep it exactly as it always has been, which is going to mean stopping things that are harmful, or we have to compensate, or we have to accept that things are going to change. Those are options. It is highly likely that things are going to change. That's basic, because we're not going to be able to conserve. And because it's just human nature, and besides that, even if we stop increasing the rate of carbon dioxide production today, we're still locked into 2 or 3 degrees We already committed ourselves. That's how much. That's going to happen anyway. So we need solutions. We unquestionably need solutions. And as always in these debates, my view, there's a balance to be struck. We need some conservation. We need some engineering. We need to reduce our dependence on fossil fuels. We have to increase our usage of other and so on. So
I mean, we have all of these climate change, these global climate change conferences, and there's one coming up in Paris, COP21 in December, and there's never been ever any agreement on how much governments should reduce CO2 emissions. So part of this geoengineering story is really the role of scientists in developing a playing card for your back pocket to put on the table if the politicians fail to make any progress in the future.
Perfect. Ladies and gentlemen, I'm afraid time has caught us up. We're officially out of time for the session, so I'm going to have to wrap everything up there. Just one last thing before we go. Mike here has been very modest in that he didn't mention he's just published a book entitled Climate Change Briefings from Southern Africa. And he's very generously offered us a copy of that book for whichever student on the course comes top at the end in terms of grade. So the top student on the course will be getting a signed, clearly, right?
Clearly signed.
A signed copy of Mike's book on climate change. It just reminds me to thank Mike for that, but to thank all the panel for giving up their time on a weekday evening. I know that you've all left your families or your social life to come down here and to talk about science for the benefit of our students. So it's wonderful, and thank you very much, guys. We couldn't do it without you. And also, of course, to thank all the students who joined us for watching it, and to say I hope you've enjoyed the session and you keep enjoying the course. And we'll see you in a couple of weeks for the next time when we're going to be discussing climate change and human issues. Thanks very much, guys. Goodbye.
Cheers.
Bye.